Hi everyone, how are you doing? Hope that you're well. I am certainly well on my end. My name is Professor Andrew Timming, and I want to extend a warm welcome to you for dropping into this lecture on multiple regression, which will unfold across three parts. This is part one. So we are 2/3 through the book. You'll recall that in the first four chapters of the book, the first 1/3, we covered the foundations of quantitative research. And then in the subsequent four chapters, we looked at bivariate statistical tests. Bivariate statistical tests meaning that there is only one X and one Y in each test. And the statistical tests that we looked at in those four chapters are the t-test, the ANOVA, the chi-square, and lastly, simple regression and Pearsons R. Now we have reached the point at which I feel that you're ready for multiple regression and, by extension, multivariate statistical methods. Multivariate methods are methods that deal with three or more variables at a time. We're going to start with multiple regression in Chapter 9. And once we're done with multiple regression in Chapter 10, we'll look at logistic regression. Chapter 11, we will look at factor analysis, and Chapter 12, we'll look at structural equation modeling. So let's start with multiple regression, probably the most commonly used method in all of statistics. Here you can see the book that we're using for this lecture series. It's entitled Applied Statistics, Business and Management Research, and it was authored by yours truly. I would urge you to first read Chapter 9 of this book before proceeding with this lecture. By reading the material, you will have a better understanding of some of the concepts that I'll be talking about, not only in part 1 of this lecture, but also in the subsequent parts 2 and 3. So without further ado, how about we jump right in and learn a bit about multiple regression analysis. So in the last chapter, in chapter 8, we learned about simple regression, and we looked at the simple regression equation, y equals bx plus a. Multiple regression is simply a multivariate extension of simple regression. And the key difference between multiple regression and simple regression is that, as I said, simple regression is a bivariate test with only one predictor, with only one independent variable, and we call that X. In the context of multiple regression, we can have multiple independent variables, multiple predictors simultaneously estimated within the equation. Now, even though we can have multiple independent variables in multiple regression, we can still only have one dependent variable at a time. So there's only one outcome variable, and that's y. So we're using a set of predictors, x1, x2, x3, etc., in order to predict our variable, our dependent variable, y. Similar to in simple regression, y in the context of multiple regression analysis always has to be a metric variable, that is to say ordinal or preferably scale level in measurement. And the reason is that multiple regression, like simple regression, is a parametric statistical test. It is predicated on the normal distribution, and therefore your dependent variable has to be roughly normally distributed. That is to say, it has to appear something like a normal curve or a bell curve. The independent variables in your multiple regression analysis, I'm talking x1, x2, all the way up to xy or xi, depending on how many variables you include in your equation, must be linearly related to y. That is to say that there must be a linear relationship between each predictor and the dependent variable. There is one exception, and that's the case of the dummy variable. And we'll talk more about this later in this lecture series. But a dummy variable is a two-category nominal variable that you can include as an independent variable in a multiple regression analysis. Yes, it violates the assumption of linearity. It is clearly not linear related to the outcome variable, but we've agreed as data scientists that we can use these types of variables. Let's look at a practical example of how we might use multiple regression to help us make managerial decisions. So imagine you're running a pizza joint. You are a restaurateur and you have your own pizza restaurant. And what you want to do is to estimate how many pizzas will be ordered tomorrow. If you had that kind of foresight, that would be useful information because then you could prepare in advance and not have much food wastage at the end of the day. So what you're trying to predict here is the number of pizzas ordered. That would be your Y variable. And then we have a series of potential predictors, independent variables, and I've labeled them x1 through x4. So x1 might be the projected temperature outside, right? If it's a very, very cold day, people might be more inclined to order a warm pizza. The projected rainfall, right? So if it's a very rainy day, people might not feel like going out. They might be more likely to order a pizza. The number of pizzas previously ordered would be a good indication of future orders. And lastly, the customer satisfaction trends. You're looking at how satisfied your customers are in the past and then projecting that into the future. And what you're doing here is you're taking all of these predictors and adding them together in order to provide a super estimate of Y, the number of pizzas ordered, that should be better than if you were to take each one of these predictors individually and predict Y. All right, so let's take another look at a research question that we could ask and answer using multiple regression analysis. And in fact, this is a research question that I have asked and answered in one of my publications, which you're welcome to have a look at. So the research question is, what are the predictors of individual job satisfaction? What we're doing is we're trying to find out what configuration of independent variables predicts how satisfied an individual is at his or her job. Now, there's almost an infinite number of predictors that you could put into a multiple regression equation, but obviously we have a limited sample size when we collect samples, and so we need to be quite parsimonious in terms of building our models. I've picked out 13 potential predictors of job satisfaction. So the contract type might be one. If you're on a fixed term contract, you might be less satisfied than if you're on a continuing contract. Working hours per week, that's self-evident. Work intensity, work-life balance, the amount of stress that you feel in your job will obviously feed into your satisfaction. Job monotony, how monotonous is your job? Similarly, job autonomy, creativity, how much creativity can you use in your role? Job complexity, employee voice, so how much voice you have in your role might influence how satisfied you are. Job insecurity, your satisfaction with pay and your opportunities for learning and development. So what we're doing is we're trying to test whether each of these predictors, each of these 13 predictors, predicts job satisfaction whilst holding the other variables constant. And of course, the dependent variable here is a measure of job satisfaction. Okay, here's another research question that we could ask and answer using multiple regression, and we'll extend this question over the next few slides so that we can break it down and show you how you would build a multiple regression model around it. The question is, what are the organization level predictors of total profits? So in this case, we have, as I said, any number of potential independent variables, but I have selected 5 that we could possibly use to predict organization level profits. The first is the percentage of the labor market with a university degree, and we'll call this x1. The second is a dummy variable. Remember, I told you a couple slides ago about the fact that we can have two category nominal variables as a predictor in multiple regression. So the second is a dummy variable measuring whether the firm is in the manufacturing sector or not, and we'll call that x2. The third is the number of years since the founding of the organization, so how old is it, and we refer to that as x3. Next, we have another dummy variable, but this time measuring whether or not the organization has access to credit, so we'll call that x4. And lastly, we have the size of the organization. So how large is it? How many employees does it have? We'll call that x5. And our dependent variable clearly in this case is some measure of total profit in dollars. So let's take a look at how we might build a multiple regression model around this question. The first thing that we want to do here is to come up with a series of hypotheses, right? Our hypotheses will spell out our expectations, our educated guesses about the types of relationships that we might expect to find when we eventually test our model. And these hypotheses typically, although not always in more complex models, they're obviously more complex than this, but typically center around a series of bivariate relationships that we might expect. So I've articulated 5 hypotheses corresponding to our 5 predictors in the model. H1, hypothesis 1, is the higher the percentage of employees with a university degree, the more profitable the organization. So this is based on the logic that if you have very skilled employees in your organization, it's likely to be more profitable. H2, organizations in the manufacturing sector are less profitable than organizations in the service sector. Now, this may or may not be true. Maybe organizations in the manufacturing sector will be more profitable. Ultimately, it will be up to the literature and existing theory to determine your hypotheses. But the important thing to remember is that whether or not it's true is kind of neither here nor there. It's okay to accept a hypothesis, but it's also okay to reject a hypothesis because either way, you're learning something about the dynamics in question. H3, the older your company, the more profitable it is. So older companies are old because they've adapted to the times and therefore they're more profitable. H4, organizations that have access to credit will be more profitable than organizations do not have access to credit. That would make sense in terms of the financing. And H5, the larger the organization, in other words, the more employees in it, the more profitable it is. Okay, so these are our hypotheses. Let's keep them in mind as we build the model. Now, you might be wondering, if we have 5 separate hypotheses, why don't we simply do 5 simple regression models to understand and test those hypotheses? And that is an option, right? You could take each predictor individually and use it to predict your outcome, in this case, y. But there are some limitations to running separate simple regression models as opposed to running one multiple regression model, which takes into account all 5 predictors simultaneously, right? So what's interesting and useful about multiple regression is that it allows us to understand or discover the pure influence of an individual predictor on the outcome, on the dependent variable, whilst holding constant the influence of the other predictors in the equation, right? So the presence of other predictors can influence how an independent variable is related to the dependent variable. And the advantage of using multiple regression is that you can look at the pure effect of each individual predictor on the outcome whilst taking into account the presence of the other predictors in the equation. And it's this ability to hold constant the influence of other predictors in order to understand the pure effect of an independent variable on the dependent variable that makes multiple regression a superior method of testing those hypotheses on the previous slide, as opposed to a series of simple regression analyses. So you'll recall from the previous chapter where we learned about simple regression, it was a simple equation. It was simply y equals bx plus a. Now, when you're dealing with multiple regression analysis, you obviously have multiple predictors in your equation, and therefore the equation itself tends to appear more complicated. So what I've done is I've created the equation here that would describe the research question at hand. So the research question is, what are the organization level predictors of total profits? And you can see here that the equation is y equals b1x1 plus b2x2 plus b3x3 plus b4x4 plus b5x5 plus a. So you should be already familiar with the general components of this equation from the previous chapter. We know that y is our dependent variable, that's total profit. We know that each x, that's x1, x2, x3, x4, and x5, corresponds to our independent variables, the 5 predictors that we're using. We know that A should be the y-intercept, so when we fit a line of best fit with these data, the y-intercept is the point at which that line crosses or intersects with the y-axis. And we also know that B corresponds to the slope, or the coefficient that describes the nature of the relationship between each independent variable and the dependent variable. And obviously, because we have 5 predictors in this equation, we also have 5 separate coefficients, or B's. And as I explained in the previous slide, each coefficient, say B1, looks at the pure effect of x1 on y whilst holding constant the remaining variables x2, x3, x4, and x5. So take a moment, press pause, and have a look through each one of these components to make sure you understand before you move on. Now, this is the equation that you would use if you are interested in predicting values of y. If you were interested in explaining values of y, you would use the equation on the next slide, but let's start with this equation here on this slide. If you want to predict profitability, so that's your dependent variable, based on these 5 independent variables after running the multiple regression, then all you would do to make that prediction is to insert your values of x1 through x5, multiply each by your coefficients, your unstandardized coefficients, that would be b1 through b5, and then add the y-intercept. So it's really simple math. Once you've actually run the equation and you've calculated your beta, your b coefficients, and your y-intercept, you simply insert the values of your independent variables, x1 through x5, do the simple math on the right side of the equation, and that will provide you with the predicted value of y on the left side of the equation. If, on the other hand, you're more interested in explaining the relationship between x1 through x5, then this probably isn't the best equation. The best equation would be one that uses standardized regression coefficients, or betas, as I explain in the next slide. So you'll recall from the previous chapter that we can use simple regression to explain the relationship between x and y, but we can also use Pearsons R, and Pearsons R is better at explanation because it says something about the strength of the relationship between x and y, right? It's always a number between -1 and 1. Well, we can do something similar in the context of multiple regression, and that's with the equation that you see at the top. So y equals beta 1 times x1, beta 2 times x2, beta 3 times x3, beta 4 times x4, and beta 5 times x5. You'll notice that there's not a y-intercept at the end of this equation. There's no plus a, and the reason is that when you standardize these coefficients, the y-intercept automatically becomes 0, so it's not necessary to put that into the equation. So this equation with the betas as opposed to the b's is similar to the last equation, but there's no longer the y-intercept, and now the coefficients themselves are not b's, they are standardized betas. And like with Pearsons R, betas are always a number between -1 and 1, where 1 indicates a perfect positive relationship, -1 indicates a perfect negative relationship, and 0 indicates no relationship at all. Of course, the strength of the relationship between each independent variable and the outcome and the dependent variable will depend not only on the beta, but also on the p-value that corresponds to it. So each x predictor will have a p-value associated with it that will tell you whether or not that particular predictor is significantly related to the outcome. Okay, thank you very much for listening to part 1 of this lecture on multiple regression. I look forward to catching you at part 2. Thanks everyone. Bye.